Hello, everyone. Welcome to the topological complexity seminar of the Applied Algebraic Topology Research Network. Today, our speaker is Soumen Sarkar, and he will talk to us on the LS category and topological complexity of real torus manifolds and Dold manifolds of real torus type. Soumen, take it away.
Thank you, John, for the invitation. And I'm happy to present my little work. So the concept LS category and topological complexity, it is well known to us. However, why I chose this topic is to advertise many new topological spaces. So since we are algebraic topologists, we are happy to explore many properties of new topological spaces. So this is a joint work with my student Koushik Brahma and Navnath and Koushik. Okay. So this definition, all of us, we know, but to complete the talk, I just put it here. So I will take like a non-normalized version. And if we cannot find such kind of covers, then we say this is infinity. So we have another. So this is, okay, if we have a topological space X, then we can consider many maps from the closed interval 0, 1 to X, and that we say like it is a free path space. So naturally we have a fibration from Px to X cross X, sending the path to the endpoints. So Fibre introduced this definition, and he said, we say that complexity, actually why it is like that. So given a two endpoints, whether we can have some continuous motion. So from that concept, this definition is very important. And we know many applications, many results are there. So it says locally we should have some sections for this path fibration. Then that number of, smallest number of those kind of open covers is called like the complexity of the space. Okay. Now, these two definitions seems very easy. However, I found very difficult to compute in many spaces. So what are the spaces we can have? So these two are like homotopy invariants. Of course, if we are having a topological space, as we are topologists, we want to know as many invariants as we want, right? Okay. Something is going on. I don't know how my page is containing the line. Okay, so if we take a point, can I just, is it okay to see the slide or something wrong?
No, I think it's okay. We can see everything.
Okay, so what we consider like a point, and then on that point, some we take projective space, and then the tower where the fiber or at each stage is like real projective space. So that is known as a generalized real Bott tower. And at some stage, if we take like Lth stage, then we say like it is Lth stage generalized real Bott manifold. So why it is generalized is like the real Bott manifold was like successive circle bundle over a point. So, okay. So this is not that much new species, but relatively new, and several properties are there. However, we don't know how to compute the exact value of the topological complexity. So I decided, okay, so what should be the motivation? Actually, behind each work, there should be motivation. So this is motivation number one. So Farber, Tabichinkov, and Uzvinesky, they showed a nice result, and it says topological complexity of real projective space is equal to its immersion dimension. So when I read like long time back, 10 years back, I was really surprised that how they prove it, and it was amazing way to discuss it. So why we should discuss? The thing is, we had this real Bott manifold, but we can see this real Bott manifold as an orbit space of a m-dimensional. Okay, if we take this Z2 as a vector space, Z2 power m, then it is a m-dimensional vector space over the finite field F2. So we have this Zm, free Zm action on this product for some m and k. And the orbit space is this one. So for example, if we take the sphere, the antipodal action, it gives real projective space. And in this paper, they used that information also. So what about for this case? So the natural question comes, is the topological complexity of a generalized real Bott manifold M equal to its immersion dimension? Of course, till now I could not get whether the answer is yes or not when K is much bigger. Okay, so this is the first motivation. Now, as I did some work in the area of torus manifold or toric topology, so what I'm interested in Z2n action on Rn. So this Z2n action on Rn is generated by reflection of the hyperplane. So considering this, Davis and Januszewski, they introduced this locally standard action sometimes back, 34 years back. So what they considered, okay, if we have manifold locally looks like Rn n-dimensional manifold. So what about if we consider the local structure with some group, having some group structure, right, or isomorphic to something which preserve the group structure. So if we take a point X, it should have a neighborhood Ux, which will be equivariantly homomorphic to a neighborhood V in Rn. So in Rn, we know it is like the open subset, the equivariant, how the equivariant sets should look like. And that is called locally standard action. Okay, I'm going to a little bit combinatorial side. So a manifold with corners is called nice if we have the condition that if we take a face of codimension k, then it has to be intersection of k many or connected component of the intersection of k many codimension 1 faces. So codimension 1 faces, sometimes it's called facets. So why this connection? This connection, because if we have locally standard action, of course, if we have action on a topological space, naturally several 2-3 things comes like orbit space. So how the orbit space should look like. Now, if the orbit space is not too nice, then it's a little bit difficult to study those manifolds. However, if the orbit space is very nice, enough, for example, like this. So these are examples. So simple polytopes is like simplices or product of simplices. So it's much more nicer, like regular or cubes, n cubes, regular n-dimensional cubes. Here I shape. So this I shape is not a simple polytope. However, it is a nice manifold with corner. Whereas teardrop, this is a this is not a nice manifold with corner because this point is a codimension 2 face. However, this is not the connected component of the intersection of two codimension 1 faces. So what they studied, okay, we'll take manifold with Z2n action, which locally resembles the action, Z2n action on Rn, and the orbit space has some combinatorial structure. So which makes life a little bit easy, but in some sense also it is not that much easy. So this every L dimension of orbits, so when we say this dimension of orbits means we are considering Z2 power n as a vector space over the field Z2a. So this is the definition. So this is called real torus manifolds. So why this real torus manifolds comes in the pictures? Okay, so in particular, if P is a simple polytope, then the real torus manifold is called small cover. Actually, Davis and Januszewicz, they studied this small cover, and more generally, some other people from China and Japan, they make it more general definition. And okay. So what should be the examples of small covers? So as we defined, like real Bott manifold, generalized real Bott manifolds. So each generalized real Bott manifolds is a small cover over this product of simplices. Okay. So these are examples of small covers. And there are many other examples which are not over small covers. For example, if we take even dimensional spheres, and suppose it is dimension is n plus 1, and Z2n acts here very naturally on the first. Okay, if we take Sn and n is even and represent it like x1, x2, xn plus 1 on the first n component, Z2n acts like component wise or coordinate wise, then that action is locally standard, and orbit space we get is like suspension over n minus 1 simplex. Okay. And that suspension over n minus 1 simplex is not a nice, it's a nice manifold with corner, but it's not a simple polytope. And this has a converse that every small cover or product of simplices is a generalized real Bott manifold. Okay, so some connections, some like manifolds, some combinatorics we are having. So what question we should ask? Right? What are the analog of this real Bott manifolds? So what we have, so suppose if n is a manifold which is having a Z2 free action, and M is another manifold, we don't care about whether it is free action or not free action, then we can consider this quotient space or orbit space. So this is, the definition is mimicking the definition of Dold manifolds. So we decided to give the name generalized Dold manifold. Now, since Don is here, so why this space came in my mind is like when I was doing postdoc with Peter in Calgary. So we were interested to find out a span of some manifolds. So he gave the paper of Don Davis. It was published in, published in Proceedings, and it was like a span of product of projective spaces. So then I went through his MathSciNet page. Then I found this paper, which is called projective product spaces. So I was a little bit curious, what does it mean? Then I saw this definition. So it came to my mind that why only this definition? We can make it a little bit more general so that we'll have as many topological spaces as we want. Okay. So this definition looks very simple, but there are plenty things to discuss. So, for example, if M is like here only 2 points or like S0, then we get the definition of Don-Davis. So, and here we are considering M is a real torus manifold, and the orbit space we are telling the Dold manifold of real torus type, because it's little difficult to distinguish what type we want. Okay. So motivation 2 is, since we are having many new topological spaces, so what are the properties we can explore? So I thought, okay, LS category and topological complexity will be the good one. So in general, we could not answer what should be the LS category of this of a real torus manifold. However, if we assume this one, that boundary of the orbit space P, if it contains a simple polytope, then we can have the exact value. But we can see that there are several situations. It might be that where, okay, this boundary of orbit space, nice manifold with corners, it is like topological boundary. So if it happens, then we get the exact value. However, in general, we don't know what to have. So now, if we have a like m-dimensional real torus manifold over a nice manifold with corner, and dimension is greater than n, and one more condition is like it is having one codimension, one face, which is a simplex. Okay, so the result is looking like what we are using, some known results, which you know, like cone length or dimensionality, or like zero divisor cup length. So this gives this one. Now, in particular, what happens if n is in this form, then the zero divisor cup length will be like this. So we can see little bit close bound. However, I don't know how to compute this kind of, this has very good structure, like, okay, in many cases, we don't know even what is the cohomologous ring of this space. Okay. So now I want to just recall some result. So the cohomology ring of a generalized Bott manifold can be given by this. So where this Y1, Yi's are like generator coming from the fibre direction. So each fibre is like a real projective space. So the cohomology of the real projective space is generated by one single element. Okay? So these Yi's are generator of the ith in the ith position, the ith fiber. Okay. And this beta JLKJ, the notation is a little bit complicated. However, this corresponds to the Stiefel-Whitney class we had in the definition of Bott tower. Right? So we had Lth Bott tower. If we want to have L plus 1th Bott tower, so what we did, it is a projectivization of some bundle. And corresponding to that bundle, each bundle, we have this Stiefel-Whitney class, right? A real bundle. So this beta JLKJ, it corresponds to that bundle direction. And this calculation comes because of the, actually Davis and Januszki's, they didn't write in this form. So they gave in a different form. So we had to use that equivalence definition. like a generalized Bott manifold is a small cover and vice versa. So we had to use that computation and some algebra to get this nice form. Okay, so which we did in another paper. Okay. So interesting part happened here that if we are having BM is a small cover over this product of simplices, then this total product is non-zero. This product in this cohomology ring. So it helps us. So it took us some time to prove it. We had to spend a good amount of time. So what we did in the previous paper, we could show that we just took two-stage Bott tower because we could not show that lemma that time. So it took us some time to make sure that this happens. It looks maybe easy, but not, difficult to compute for some, in generally. And that helps us to have this lemma like a lower bound using the zero divisor cup length. So, and what should be the upper bound? Right? Problem happens like we don't know how to make this exact value. So even though there are plenty of nice bundles over this Bott manifold that we can make it, but how to use those bundle structure to get the exact value, we are not sure. So if it is a small cover, so that means it is a Bott manifold, real Bott manifold over this product of simplices, then the topological complexity should be at least this much. So it does not matter whether it is a product of RP1, RPN1 or RPN2. In general, we can have it. So if it is just product, we can use the product formula and we can get it maybe much better bound using the result of fibre and others. Okay. So how much we can reduce from the dimensionality bound. So if it is a small cover over the product of n simplices and each nj is like odd, then we can up to k. If k many are having odd dimensional simplices, then we can reduce k. So we can say that topological complexity of this small cover is nothing but bounded by 2n minus k plus 1. Okay, here notation is a little bit, we are introducing lambda, but I didn't say what is lambda. Lambda comes naturally. It is it depends on the isotropy subgroup of corresponding to a facet, codimension 1 faces. So that is a notation by Davis-Janusz-Quiz. Okay, so I need to discuss little bit equivalent LS category. So if we have a space having G action, then a G invariant open subset, we say it is like a G categorical if there exists a G homotopy. So that means this map has to be preserving the G structure. So on I means a closed interval 0, 1. So on I, G action is trivial. And what happens at each X, this one, so at 0th level, it is identity. At 1th level, it has to be a subset of an orbit. So given that, one can define equivalent LS category, which I think it appeared first in the paper of Marchantuis a long time back, 1989. So it's like similar definition as LS category, whereas those open cover has to be G categorical cover, which we know very well. Okay, and if no such covering exists, then we say this is infinity. Okay, so if we are having an m-dimensional small cover, so what is a small cover? This is also a real torus manifold when the orbit space is a simple polytope. So simple polytope means like it is having nice, it is a convex structure where each vertex is the intersection of n many. If the dimension is n many codimension 1 hypersurfaces. Okay. So what assumption we are considering that tau is an involution. If the fixed point set corresponding to this involution is path connected and this involution commutes with the Z to N action, then we can have that equivariant category is equal to n plus 1 exact value. And there are many such kind of involution, given that this is an n-dimensional small cover. Okay, we are using this polytope structure heavily to have it. So whether this result is true for more general case, we don't know. Okay. So what about the LS category of some generalized Dold manifold? So here it is, we can have this cone length as a lower bound. So if we have this Dold manifold of real torus type, where P1, P2 comes from the spheres, so this is very particular case, then we can have this lower bound. However, if we take the small cover, M is a small cover of dimension n and it satisfies the hypothesis of the previous theorem, then we can have the exact value. So it says the LS category of this space is this one. What about for other cases? As I told you, we don't know how to make it. Okay, as a note, I want to say that Jesus also did some work in a different direction, not considering the Z2 action, but finite group action on product of spheres. So,
Soumen, could I ask, what does retractable P mean on the previous slide?
Why it is not going the previous slide? Sorry, I just need to.
No,
This
now
one?
the next slide. The next slide.
Okay.
Yeah, up at the top, over retractable P.
Okay. Okay, so that means, I mean, if it is phase acyclic, so in some sense, does it make sense? So, I mean, we can contract it. So P is a nice manifold with corner. So its homology is 0. All homology is 0. Or homotopy is also 0. So that in that sense, it is retractable.
Oh,
Is it okay?
I see. Okay.
So for example, so nice manifold with corners, it can have holes. Like if we take a simple polytope like a square and we delete the neighborhood interior from the interior of another triangle, then we get a nice manifold with corner, but it does not satisfy this condition. So phase acyclic by retractable means.
Okay, that's great. Thanks.
Thank you. So RPN, I mean, real n-dimensional real projective space. This is also a small cover. So now, if we are having a small cover M, which can be written as a connected sum of two small covers, one is RPN, then we can have this nice lower bound and upper bound, which looks like very tight bound. But in general, we don't know whether how much we can have it. The main important things I want to note, for any real torus manifold, we can have plenty of line bundles over here. But whether those line bundles will help us to make the lower bound much better, I'm not sure. It might be. Okay. And in particular, what we have, if M is a small cover over product of simplices, and each ni's and P, also P1 has to be odd, then we can have the good upper bound. So it can be reduced from the dimensionality condition, dimension bound. So TC of this Dold manifold. So now we are taking only one component, P1. So that means that in the second component, we are taking SP1, P1 dimensional sphere. Then we can have this upper bound. Okay, so my talk was very short. Thank you for your attention.
Okay, everybody, if you would unmute.
I want to.
Are there any questions?
I have a comment. So I've been interested in a problem of finding the largest, finding manifolds with the largest possible dual Stiefel-Whitney class. I have a archive posting very recently about this, and I have used as my examples, I've got the best results using real Bott manifolds, but I've also considered the generalized real Bott manifolds, and I've considered the generalized Dold manifolds of the paper of Soumen and Svengroski. And so I'm sort of looking for other families of manifolds to test out. So I would need to be able to compute Stiefel-Whitney classes of families of manifolds. And so I'm looking for suggestions, and you don't have to have it right this minute, but if you think of something, you could email me with a suggestion. And I'll also comment that, oh, that was for excuse me, I forgot to say orientable manifolds. For just regular manifolds, it's just products of 2-power real projective spaces give you the best result. But for orientable manifolds, find one with the largest possible dual Stiefel-Whitney class. And then there's an analogous question for spin manifolds. And so I know that to have a spin manifold with a dual Stiefel-Whitney class equal to the dimension -2, it happens if and only if n is a 2-power. But I hadn't been able to find an example. And so then just 2 days ago, I asked ChatGPT for an example, and it came up with a good example. It's the homogeneous space, which is the quotient of the exceptional Lie group G2 mod the subgroup SO4, and that works. And how ChatGPT ever found that is amazing. So anyway, if what I'm saying here is of any interest to you, either to work on yourself or to suggest families of manifolds to me, you can see the paper on the archive or on my website. It's been submitted for publication. So that's my comment.
Thank you, Don. Yes, actually.
And Don, if you have any of the extra conditions that Soumen places in different theorems, does that help you at all?
Well, I don't understand small covers that well. I don't understand them at all. But I know the cohomology of the generalized real Bott manifolds, and I can work with that. And I did that for all the 12-dimensional generalized real Bott manifolds and didn't come up with an example. And I know that those are small covers over products of simplices, but I don't know anything more about small covers than that. And I probably should. But I mean, the two papers and I've seen Soumen has an archive posting of related to what he's been talking about here, and I looked at that yesterday or the day before, and so that's helpful to me, and perhaps I have to study that some more.
Actually, the main motivation was your paper that, and the question is how to find out the span of this kind of manifold. So like,
Yeah.
for example, for RPN, we know it is same as span of SN, but if we make it a little bit more, then we don't know how to make it. And the Stiefel-Whitney class computation, it helps to do that. And some of your results also. So that, but in many cases, we could not be able to find the Stiefel-Whitney classes. So for example, if we have several nice line bundles, then it is possible to say what will be the Stiefel-Whitney class, the total class of that. But I will go through your paper. Yes, that interesting problem. Another things to find out what will be the span of this kind of manifolds.
Yeah, you can also approach it not by computing Stiefel-Whitney classes, but by computing the anti-automorphism of this Dienrod algebra can give you the kind of information that I would want to, and I think that's what I do mostly in my paper. So yeah, if you have any thoughts or comments on that, send me an email.
Yes, thank you.
Okay, any other questions? I have just one general one. For these types of manifolds, do we know anything about the universal cover? I ask because you see, a lot of your results and assumptions lead to the category being the maximum. But when the category is the maximum, that's the same as, well, not this equivariant one, but ordinary category. That's cat 1, which is the sectional category of the universal cover. So I guess I would like to see or understand what that might be.
Okay. So in most of the cases, if we take a real torus manifold, it is not simply connected. So the name suggests like a generalization of real projective toric varieties. Smooth.
Well, that's right. So it has a universal cover then.
Correct. So it is not simply connected. So it has this universal cover, and corresponding to that, we can make the universal cover for this Bott Dold manifold of real torus type. So we can just make it using that.
Is there anything special about the universal cover?
I never thought about it, but
okay.
So what happens, as I mentioned, like corresponding to a nice manifold with corner, we have some spaces called real moment angle manifold. So on that real moment angle manifold, there are some free Z to K action, so that the quotient space will be like real torus manifolds. And in many cases, that real moment angle manifold is simply connected. Okay. However, it is not exactly the universal cover because, okay, in many No, sorry, I am little wrong because, okay, so that a real moment angle manifold is a universal cover because it is simply connected. We can make it. So for example, take RPN, then if the dimension is more than 1, then we are having antipodal action. So it is a universal cover. If we take product of, or like, as I mentioned, that if we take generalized Bott manifold, then there is a covering, which is a product of spheres. So that will be an universal cover. So the universal cover of this space is like a moment angle manifold, and many studies are happening on that moment angle. In particular, we can think it as a like polyhedral product spaces. So
Okay, thanks. Any other questions?
thank you.
Anything at all? Well, if not, let's thank our speaker again.
Thank you
And
so
I'll
much.
stop the recording. And if anybody has anything else,